Picture Earth 4 billion years ago. No beaches, no mountains, just one endless ocean stretching to the horizon. If aliens had visited then, they might have thought our planet was a giant water droplet with commitment issues. But beneath those crushing waves, something was already brewing. The first whispers of rock that would one day become continents. Imagine standing on a ship in the middle of the Pacific Ocean. Now, erase the sky's blue and turn it into a constant haze of steam. Stretch the sea in every direction until there's no hint of land, not even a drifting leaf or a curious seabird. That's what early Earth looked like. A planet swallowed entirely by its own ocean. No continents, no islands, just a world-sized puddle spinning under a thick, brooding atmosphere. You could call it peaceful if you ignored the fact that everything was constantly boiling, hissing, and belching gases from below. Back then, the sun was younger and dimmer, shining about 70% as bright as it does today. But Earth didn't notice. It had its own drama going on. The surface simmered with volcanic heat, while the atmosphere was choked with steam and carbon dioxide. The air would have been thick enough to chew, and the rain that fell was more like liquid fire than fresh mountain dew. Yet, through all that chaos, oceans managed to form. Vast, global seas that wrapped the planet in blue. If you could fly above it, Earth would have looked hauntingly beautiful, a shimmering marble covered in swirling clouds and mist. But it wasn't the kind of place you'd want to vacation. Beneath the waves, water was hot and dense, saturated with minerals leached from a restless crust. It was an alien ocean, one without fish, coral, or seaweed. There was no sound of waves crashing on a beach because there were no beaches. The only noise came from the deep, where hydrothermal vents hissed and magma cracked open the ocean floor like the planet was sighing in its sleep. This water world was both familiar and strange. Familiar because water itself is life's best friend. It dissolves, mixes, carries, and connects. Strange because life hadn't yet taken advantage of that gift. The ocean was like a stage before the actors arrived, the set already built, lights dimmed, curtain ready to rise. The chemistry was there, the energy was there, and all the ingredients were swirling in that vast soup, waiting for something extraordinary to happen. And deep below, it was happening. Slowly, invisibly, but unstoppably. Beneath miles of crushing water, the interior of the planet was shifting and cooling. The heavy materials, mostly iron and nickel, sank into the core. The lighter silicate rocks floated above, forming the first thin crust. It was fragile, constantly recycled by heat and pressure. But it was the foundation of everything that would come later. Earth, in its watery youth, was already sketching blueprints for continents, even though it didn't yet know how to build them. The idea of a water-covered planet might sound like paradise, the ultimate beach world, but it came with serious drawbacks. Without continents, there were no tides as we know them, no rivers carving valleys, no mountains feeding nutrients into the sea. The planet's surface was geologically quiet in some ways, but furious in others. Submarine volcanoes erupted constantly, belching out minerals and gases that changed the chemistry of the oceans. Lightning storms crackled above, fueled by the thick atmosphere, striking the sea in endless flashes that may have sparked complex molecules into existence. Earth, in its own way, was running a cosmic experiment. How do you take a sterile planet and turn it into a living one? Step 1. Cover it in water. Step 2. Stir vigorously with heat and lightning. Step 3. Wait a few 100 million years. If we could watch this process in time-lapse, we'd see the ocean shimmering under an orange sky. Waves the size of skyscrapers rolling endlessly, and occasional volcanic islands rising briefly before sinking back beneath the waves. Each eruption, each cooling period, was part of a slow planetary heartbeat. The crust beneath the water was thin, constantly cracking and healing. Every bubble of magma that rose up was a promise of something new. A clue that someday land might win a small battle against the ocean. But for now, water ruled everything. It shaped the planet's temperature, absorbed the sun's light, and dictated the chemistry of the surface. Without land, there was no place for erosion, no source of dust, no soil. The planet was, quite literally, smooth, and yet that simplicity hid enormous potential. Because in this ocean, minerals were dissolving, elements were colliding, and molecules were forming new bonds. Hydrogen met oxygen, carbon met nitrogen, and the dance of atoms began the first slow steps toward complexity. Somewhere in that vast, dark water, the seeds of life were being mixed, not by design, but by chance. It's humbling to think that our continents, our mountains, even our cities, all began beneath that endless ocean. The same planet that once had nowhere to stand eventually built everything we now stand on. Earth's early water world wasn't a mistake. It was a masterpiece in progress. A world that began as a giant puddle, learning, drop by drop, how to become a home. So, when we call Earth the blue planet, we're not just describing its color. We're remembering its origin story, a time when it was all blue, all water, all potential. The land would come later, bursting through the waves in a slow geological rebellion. But before the continents rose, before mountains touched the sky, Earth was a dream floating in its own reflection, a lonely ocean waiting to discover itself. Before the water came, Earth was basically a lava lamp turned up to 11. The surface shimmered with molten rock, volcanoes belching gas like chain-smoking dragons, and temperatures so high that any ocean would have boiled on sight. But as the planet cooled, steam condensed, and rain began. Not for days or years, but for millions of years. Earth, in short, went through the most dramatic cool-down in history. Before Earth was blue, it was blazing. 4.5 billion years ago, the newborn planet wasn't so much a world as it was an endurance test for matter itself. Everything glowed. The surface boiled with molten rock, the sky burned with fire, and even shadows would have melted if you could have stood there, though stood might not be the right word for a world that hadn't invented solid ground yet. You'd be vaporized before you had time to regret the decision. It began in chaos. Earth's creation was not gentle. It was an act of violence. Dust and rock collided in the early solar system, drawn together by gravity like an ever-growing cosmic snowball. Each impact released unimaginable energy. The planet grew by being pummeled, and every new collision reheated what little progress it made toward cooling. You could say Earth's childhood was explosive, and you'd be completely right. At some point, it got its biggest and most fateful hit, a collision with a Mars-sized body we now call Theia. That crash was so catastrophic it vaporized part of Earth's crust and sprayed molten debris into orbit. Those glowing fragments eventually clumped together and cooled, giving us the Moon, Earth's lifelong companion and constant reminder that space traffic used to be a real problem. After Theia's impact, Earth was more inferno than planet. The crust was gone, replaced by a deep global magma ocean that might have been hundreds of kilometers thick. Imagine an entire world glowing red, its surface shimmering with molten silicate waves. The air above wasn't really air at all, just a choking mix of metal vapors and gas, swirling in a sky the color of iron. It was the ultimate hot mess, and yet, hidden inside all that destruction, the foundations of our planet's future were already being laid. Inside that molten ocean, gravity went to work sorting things out. The heaviest elements, iron and nickel, began to sink toward the center, forming the dense metallic core. Lighter materials floated upward, layering themselves into what would one day become the mantle and crust. Earth was performing the cosmic equivalent of stirring soup and waiting for it to settle. That internal organization, chaotic though it looked, set the stage for everything from magnetic fields to plate tectonics billions of years later. But let's not get ahead of ourselves, because at this point, Earth was still far too hot for any of that to matter. The surface temperature may have exceeded 2,000 degrees Celsius, and the atmosphere was a soup of steam, carbon dioxide, sulfur dioxide, and traces of ammonia, all the ingredients of a nightmare sauna. Volcanic activity was relentless. The young planet burped, hissed, and roared, spewing fountains of molten rock into an already glowing landscape. Over time, and we're talking millions of years, not weekends, the heat began to leak into space. Slowly, painstakingly, the magma cooled. Crystals began to form, and the first thin crust solidified on top of the molten sea. It wasn't sturdy. It cracked constantly, letting magma bubble through in spectacular glowing eruptions. You could call it the ultimate version of lava lamp aesthetic. The atmosphere changed too. Those chain-smoking volcanoes were releasing gases that would one day make oceans possible. Every eruption exhaled steam into the air, and because there were no plants or oceans yet to trap it, that steam just kept building. Earth was wrapping itself in a dense, steamy blanket that kept heat in, but also carried the potential for transformation. As the surface cooled further, that thick vapor started to condense. And then it began to rain. Not the kind of drizzle you complain about on a gray morning, but rain so intense it could reshape a planet. For millions of years, water poured from the sky in unrelenting torrents. Each drop that fell hit molten rock and exploded into steam, releasing bursts of energy and slowly wearing away the crust. The noise must have been deafening, thunder rolling across continents that didn't yet exist, lightning flashing across a sky filled with volcanic smoke. Those endless rains were Earth's first great act of renewal. They cooled the surface, filled basins with liquid, and began the long process of sculpting what would one day become oceans. Every drop carried chemical traces from the atmosphere, and when it hit the molten minerals below, new reactions took place. Hydrogen met oxygen. Sulfur met iron. The beginnings of the chemical alchemy that would eventually give rise to life. But during this time, life was still billions of years away. What existed was a world caught between fire and water, a planet learning balance. The solid crust thickened, the atmosphere thinned, and volcanic eruptions became less constant. Steam continued to rise, condense, and fall again, cycling endlessly until much of that vapor finally became the liquid oceans that would define the next era. If the early molten earth was a fiery inferno, then the onset of rain was its first deep breath, the moment the planet began to cool enough to sustain stability. It was like watching a fever break after an eternity. Beneath the steam, glowing red plains turned dark and solid, and rivers of molten rock hardened into the first real stones. For the first time, Earth had a skin thick enough to hold its own against the heat below. And yet, the story of this cooling wasn't just about temperature. It was about transformation, about chaos finding structure. The same forces that once destroyed now began to create. The violence that forged the planet also gave it the energy, materials, and dynamism it would need to one day support life. The fire wasn't the opposite of life. It was the rehearsal. So, when you imagine early Earth, don't picture a quiet sphere slowly spinning in the dark. Picture a raging, glowing world, cracking and healing, burning and cooling, a planet in the middle of a billion-year metamorphosis. And when those first drops of rain finally fell on that molten landscape, sizzling into vapor, the universe itself might as well have whispered, "Now, let's begin." Imagine clouds so thick the sun was just a rumor. The newborn Earth's atmosphere was full of steam and volcanic gases, and when it finally cooled enough, the sky unleashed a biblical-scale downpour that filled basins, craters, and crevices until the planet drowned itself. You could call it the original global flood, minus the arc, plus a lot more hydrogen. There's rain, and then there's the rain. Not a storm that ruins your picnic, a storm that builds an ocean. Picture a world wrapped in a suffocating fog of steam and gas, the air so heavy you could almost swim through it. Above, thunder rumbled across a sky you could barely see. The sun, though it still burned fiercely in the heavens, might as well have taken the day off. The newborn Earth was shrouded in clouds so dense that sunlight struggled to reach the surface. It was less sunrise and more permanent apocalypse glow. After millions of years of fire and magma, Earth had finally cooled just enough for vapor to condense. The atmosphere, swollen with steam released by volcanic fury, began to reach its breaking point. Every droplet that formed in those monstrous clouds fell into an atmosphere already thick with moisture, where it grew heavier, merged with others, and then finally plunged toward the ground. The first rain in history began not as a gentle drizzle, but as a cosmic tantrum. It rained with the patience of geology and the enthusiasm of a planet trying to reinvent itself. The water struck molten rock, evaporating instantly into more steam, which then rose, cooled, and fell again. This endless loop created storms of unimaginable ferocity. The sound would have been a continuous roar, raindrops hissing, steam exploding, thunder rolling across the sky in an endless percussion of creation. The planet was boiling and cooling simultaneously, a giant cauldron with lightning for seasoning. The rain did not stop for days or decades or even centuries. It fell for millions of years, sometimes slowing as the atmosphere shifted, sometimes raging harder when new volcanic bursts added more steam to the mix. Each drop carried with it traces of dissolved gases, carbon dioxide, nitrogen, sulfur compounds, that reacted with the cooling rock below. The crust, still fragile from its fiery birth, began to change color and composition under this relentless assault. Where molten plains once glowed, solidified minerals now shimmered with new hues, reshaped by chemical weathering. Eventually, as the surface cooled and solidified, the water began to stay. It gathered first in the planet's natural scars, the basins, cracks, and craters left behind by eons of cosmic impacts. Over time, these small puddles became vast interconnected seas, merging until there was no land left dry. The world had gone from molten red to reflective blue, from glowing to glistening. Earth had effectively flooded itself. But this was no sterile flood. The deluge was sculpting the first traces of topography. Each raindrop that struck at the surface wore it down a little more, carrying minerals and particles into the deepening basins. Rivers began to form, though the word river might be too polite for what were essentially roaring torrents of boiling runoff. The surface crackled with thermal contrast, lava fields and steam vents alongside pools of newly formed water. It was a planet in mid-transformation, switching from fire to fluid. The atmosphere above was still a chemical experiment in progress. There was no oxygen yet, no ozone to block harmful ultraviolet light. Instead, the sky was a greenhouse of carbon dioxide and water vapor, trapping heat and giving the planet a thick, humid personality. Temperatures would have remained scorching, but the surface was no longer pure inferno. It was warm, wet, and alive with energy. Lightning split the sky constantly, igniting new reactions in the turbulent air. Each flash could have forged complex organic molecules, the very building blocks that much later would give rise to life. The rain also played a crucial role in shaping Earth's atmosphere. As it fell, it dissolved gases and minerals, dragging them into the oceans and removing them from the air. This chemical give and take began balancing the carbon dioxide levels and altering the planet's climate trajectory. It was, in essence, the first act of planetary engineering, performed not by intelligent life, but by sheer physics and patience. As the ocean deepened, the sky began to clear. The heavy veil of steam thinned just enough for sunlight to pierce through. Imagine that moment, after millions of years of unbroken storm, when the first golden light touched the waves. The ocean would have shimmered with reflections never seen before, its surface glittering like liquid glass. The color of the world had changed. It was the dawn of blue. But the rain never fully ended. Even as the planet stabilized, water continued to fall in cycles, feeding evaporation and condensation, carving valleys, and cooling the crust further. It wasn't just an episode. It was the birth of the hydrological cycle itself. The same process that fills your coffee cup today was born in those apocalyptic centuries of storm. Every droplet that hits your window during a thunderstorm carries the ghost of that ancient rain within it. This endless downpour also had an emotional quality, if one dares to personify the planet. Earth, having been forged in violence, was finally soothing itself. The rain was a balm over its scars, sealing cracks, taming fire, and laying down the foundation for everything to come. It was as though the planet exhaled after eons of holding its breath. And in that exhale, something extraordinary happened. Stability. The surface temperatures began to even out. The thick, wet clouds that once hid the sun started to drift apart. Water vapor balanced itself between ocean and sky. For the first time, Earth had found a rhythm. Rain, evaporation, condensation, repeat. The chaos was still there, but now it was structured, cyclical, meaningful. The flood that had once threatened to consume the planet instead became its defining feature. From that endless storm came the seas that cradle life today, the clouds that paint our sunsets, and the rain that connects every ecosystem on Earth. The planet that had once been pure fire now shimmered with blue oceans and a silvery sky. The deluge didn't destroy the world, it created it. And when the final great storms faded, leaving behind oceans that stretched from pole to pole, the earth looked up through its thinning clouds and caught its first clear glimpse of the sun. That light danced across the waves, and for the first time in the history of the universe, our planet reflected. When the last great storms eased and the planet settled into its watery rhythm, Earth was quiet, at least from a cosmic perspective. On the surface, there were no continents yet, no trees, no light beyond the dim glow filtering through miles of ocean. But beneath that dark, endless sea, the planet was humming with activity. Deep down, where sunlight had never touched, Earth was busy experimenting. The seafloor was still young and restless. Cracks ran through it like veins, and through those cracks, hot water surged from the planet's molten heart, and these were the first hydrothermal vents, enormous underwater chimneys spewing superheated water laced with minerals. They formed wherever seawater seeped into the crust, met magma, and came rocketing back out, now charged with the chemistry of the deep. You could think of them as Earth's original laboratories, and they were open for business 24 hours a day. At first glance, the vents might have looked hellish. Clouds of black and white smoke billowed from their openings, painting the surrounding water in eerie shades. The temperatures near their mouths could exceed 400 degrees Celsius, hot enough to melt metal, yet just meters away, the water was near freezing. This extreme contrast created a dynamic playground of energy, gradients in temperature, chemistry, and pressure. And life, or something suspiciously close to it, thrives on gradients. Here's where things get interesting. Those hot fluids weren't just water, they were brimming with chemicals like hydrogen sulfide, methane, and iron. As the vent water hit the cold ocean, these compounds reacted and formed mineral-rich structures, building towers and chimneys from the seafloor up. Within those mineral walls, microenvironments emerged. Tiny chambers where chemical reactions could happen safely, shielded from the chaos outside. Imagine millions of microscopic cauldrons bubbling away in the dark, each one trying a new recipe for complexity. And complexity is exactly what was brewing. Inside these mineral pockets, simple molecules collided and combined, forming more elaborate compounds, amino acids, lipids, and the first self-organizing chemical systems. It wasn't biology yet, but it was chemistry on the brink of becoming something more. Carbon from the volcanic gases bonded with hydrogen from water, creating the precursors of organic molecules. Sulfur and iron acted as catalysts, speeding up reactions the way chefs use heat to caramelize sugar. It's funny to think that the first steps toward life might have happened in what we'd now call toxic waste zones. But these vents, with their metallic taste and poisonous fumes, had everything early chemistry needed: energy, minerals, and a steady flow of ingredients. The universe had handed Earth the perfect laboratory kit, and then just left it alone for a few 100 million years to see what happened. At the edges of these vents, something remarkable began to occur. Certain minerals, like pyrite and olivine, could store and release electrons, creating natural electrical currents. These little sparks of energy acted like matchsticks, igniting reactions that built more complex molecules. Imagine the seafloor flickering faintly with invisible lightning. Not enough to light the dark, but enough to set chemistry in motion. As the reactions continued, some molecules began to form membranes. Thin, bubble-like structures that could trap other molecules inside. These were the first primitive containers, precursors to cells. Within them, chemical reactions could take place more efficiently. You might say that life's earliest attempt at organization was figuring out how to keep its stuff in one place. These proto-systems began feeding off the gradients around them. The heat from below, the cold from above, the chemical flow from the vents. Each one was a little engine running on imbalance, the universal secret of all living things. And over time, those engines became more sophisticated. They began copying certain reactions, stabilizing certain molecules, creating the first patterns that resembled metabolism. This wasn't design. There was no plan, no divine blueprint. It was the raw logic of physics and chemistry, energy-seeking pathways, atoms seeking balance. But every now and then, one of those accidental arrangements worked better than the others. It lasted longer, produced more copies of itself, and so, by pure chance, persistence began to look a lot like survival. The first whispers of evolution were echoing through the dark, long before DNA ever came to the party. Meanwhile, the vents kept roaring, painting the seafloor with metallic rain and plumes of mineral dust. Over millions of years, they built vast landscapes, forests of chimneys rising from the abyss, surrounded by shimmering halos of chemical reaction. Each vent was an island of potential in an otherwise lifeless ocean, like campfires burning on the bottom of the world. And, eventually, something incredible happened. Within one of those microenvironments, some combination of molecules, maybe a self-replicating RNA strand, maybe something even simpler, achieved stability. It could make copies of itself using the resources around it. It didn't live in any sense we'd recognize, but it crossed the line between chemistry and biology. It was the moment the universe took a deep breath and said, "All right, let's see where this goes." From that moment onward, Earth was no longer just a planet. it was a process. The oceans that had once been empty now held potential. The vents that once belched poison now hosted pioneers. The spark had caught. If you could drift through those ancient waters, you would see nothing, just darkness and the faint glow of mineral plumes. But invisibly, silently, the gears of life had begun to turn. Atoms had found a way to organize, to persist, to remember. All of it, every forest, every coral reef, every heartbeat, began there beneath crushing miles of ocean at the mouth of a vent that had no idea what it was creating. Earth's first act of life wasn't a miracle. It was chemistry gone gloriously rogue. From the outside, early Earth looked calm for the first time in its young, chaotic life, an endless blue marble wrapped in clouds, gently rotating beneath a dim sun. But inside, it was anything but peaceful. Beneath those quiet oceans, the planet's heart was still raging with heat. Radioactive decay deep in the mantle churned like a cosmic furnace, and the molten rock below the crust flowed in thick, slow motion. Earth might have looked serene, but under that glossy blue skin it was more like a pressure cooker humming at full power. To understand what was happening then, imagine taking a pot of soup off the stove but leaving the burner on low. The surface starts to cool and form a skin, but underneath the stew is still bubbling and restless. That was the early Earth's mantle, a vast, viscous sea of semi-molten rock, constantly circulating, constantly moving heat from the deep interior toward the surface. Those currents of molten rock were the planet's first convective systems, the slow, powerful heartbeat that would one day drive tectonic plates, build mountains, and tear continents apart. At this stage, the crust above the mantle was thin and fragile, more like a film than a shell. It cracked easily under the strain of rising magma, opening fissures that spewed out minerals and gases. Each eruption cooled and hardened, adding new layers of rock to the ocean floor. Slowly, piece by piece, the planet was growing a skeleton beneath the waves. But it wasn't uniform. Not all magma was created equal. Some portions were richer in iron and magnesium, dense and dark like basalt, while others were lighter, full of silica and aluminum. As heat and pressure continued to work their geological magic, these minerals began to separate. The heavier materials sank, drawn toward the core, while the lighter ones started to accumulate near the surface. It was as if Earth was sorting itself from the inside out, a planetary centrifuge refining its ingredients. This process of differentiation was the foundation of everything that followed. It didn't just create the layers we know, crust, mantle, core. It also planted the seeds of continents. The lighter materials, which resisted sinking, began to collect in patches. Over millions of years, these buoyant rock clusters thickened and became the first stable fragments of continental crust. They weren't continents yet, more like ghostly outlines of future land masses, hidden under kilometers of water. Deep in the mantle, convection currents kept stirring. Hot rock rose from below, cooled, and then sank again in slow, endless cycles. Where these plumes of heat reached the crust, they caused partial melting, a process that changed the chemical flavor of the rock above. Each melt extracted lighter, more silica-rich material, concentrating it in the crust. Layer by layer, the planet was refining itself into something more complex, like a blacksmith hammering ore into steel without realizing what he's making. And then there were the fractures. The crust wasn't a smooth, unbroken shell. It was a patchwork quilt of cracks and ridges constantly being torn open and resealed by molten rock. These fractures acted as vents, letting the planet release pressure, but they were also creative. Every time magma oozed through, it cooled into new rock, thickening the crust and changing its composition. The process was violent, slow, and beautifully chaotic. Geology's version of evolution through trial and error. You might think of the mantle as a secret sculptor, shaping Earth's bones in total darkness. It wasn't in a hurry. Over tens of millions of years, it built ridges, crustal domes, and strange buoyant blobs of rock known as proto-cratons, the embryos of future continents. Each one was born from deep heat and patient movement, solidifying just enough to resist being recycled back into the molten abyss. This hidden architecture was also responsible for one of the planet's most defining features, its magnetic field. As the iron-rich core continued to differentiate and churn, it created a dynamo effect, a self-sustaining magnetic shield that protected the young planet from solar radiation. Without it, the oceans could have been stripped away by the solar wind, turning Earth into a barren husk like Mercury or Mars. In other words, while the planet's interior was busy forging structure, it was also building protection. Over time, the mantle's chemistry evolved. Each eruption changed the crust slightly, enriching it with different minerals and elements. Silica became more common, forming lighter and more buoyant rocks. The seafloor thickened in places, while in others, new cracks opened in to let heat escape. It was a planet-wide game of whack-a-mole. Every time one area stabilized, another burst open. Yet beneath that chaotic surface behavior was a clear direction: upward growth. Every geological breath, every bubble of magma, every convection current was helping the crust mature. The bones of the future continents were taking shape invisibly, waiting for their grand reveal. The mantle's slow, persistent labor was creating platforms that would one day lift above the waves and host everything from ferns to cities. Even in its infancy, Earth was displaying one of its most powerful instincts: self-organization. Out of molten disorder, it was constructing order, layers, patterns, feedback systems. The planet didn't have life yet, but it already behaved like something alive, a restless, self-regulating organism that evolved over time. And that hidden skeleton beneath the water, the ancient crust, stitched together by molten seams and sculpted by pressure, was its backbone. The continents, when they finally emerged, wouldn't appear by magic or miracle. They'd rise because the planet had spent eons preparing for them, crafting their foundations atom by atom in the dark. So, while the ocean world above seemed still, the true drama was unfolding below. Deep currents whispered through the mantle, carrying the memory of heat and movement. Minerals drifted and settled. Chemistry became architecture, and the earth built strength in secret. Someday, those bones would break the surface and change everything, but for now, they remained hidden, silent, and full of promise. Earth was dreaming in stone, and its bones were growing beneath the waves. After hundreds of millions of years of relentless sculpting from within, Earth finally decided to show its first bit of skin. It happened slowly, almost shyly, not with the drama of an explosion or the flash of a birth, but with the quiet emergence of rock through water. The ocean that had once swallowed everything now rippled around the first islands, jagged, steaming, and strange. The planet had been a world of liquid and vapor. Now, for the first time, it had something that could cast a shadow. Imagine standing on one of those early peaks, though standing might be generous, since the surface would have been barely solid and hotter than a summer sidewalk in hell. You'd look out and see nothing but horizon. No birds, no waves, no sound but the hiss of escaping steam. The water below would stretch endlessly, thick with minerals, and the sky above would be a pale haze of gas and mist. Yet what you were standing on was something miraculous. The first dry land in Earth's history, a tiny outpost in an otherwise liquid world. These early patches of crust weren't continents as we know them. They were more like flecks of granite caught in the bubbling stew of the mantle, small, irregular, and constantly reshaped by heat and pressure. Geologists later gave them the dignified name cratons, but at this point they were really the planet's geological toddlers, wobbly, unpredictable, and covered in bruises from every eruption and impact. Their formation was a balancing act between heat and buoyancy. As the mantle convected below, it melted and remelted sections of rock, each time producing new materials. Lighter, silica-rich magma slowly rose to the surface, cooled, and hardened into granitic crust. The kind of rock that floats higher on the mantle compared to the denser basaltic crust that forms the seafloor. Over eons, these floating chunks began to stabilize. When they grew thick enough, they resisted sinking back into the molten abyss. The result was geology's first act of defiance. Rock that refused to drown. These cratons began as isolated microcontinents, scattered across the planet like crumbs on a blue tablecloth. Some may have been the size of modern-day islands, others mere ridges just peeking above the waves. Between them stretched thousands of kilometers of deep ocean. They were lonely, battered by constant rain and volcanic fallout, eroded by primitive chemical weathering before rivers even existed. And yet, they endured. Each craton carried a story written in its minerals. The zircons embedded within them, tiny, glittering crystals only visible under a microscope, became Earth's first record keepers. They trapped within their atomic lattices traces of oxygen isotopes, pressure, and heat signatures, silent witnesses to the planet's transformation. Billions of years later, geologists would study those zircons and realize they were holding the earliest geological diary ever written. But in their own time, these cratons were far from peaceful. They weren't content to sit quietly at the surface. They drifted, collided, and reshaped one another under the influence of mantle currents. Each impact fused or fractured them, creating mountain-like ridges that rose briefly above the sea before crumbling away. It was a chaotic game of geological bumper cars. Some cratons sank back into the depths, swallowed by new magma. Others survived, growing thicker and tougher with every collision. Survival of the fittest wasn't just for biology. It started with rocks. As they stabilized, these abundances began to influence the ocean around them. The newly exposed land altered local chemistry. Rain, rich with carbon dioxide, fell upon the raw rock, dissolving minerals and carrying them into the sea. These minerals, calcium, silica, iron, became nutrients for the future. They changed the ocean's composition in subtle ways that would, much later, matter immensely to life. Even in their infancy, continents were already changing the rules of the planet's chemistry. From above, the scene would have been surreal. The blue of the ocean interrupted by scattered patches of brown and black, fringed with mist from geothermal vents. Lightning flickered across the sky, illuminating the glistening rock faces and boiling tidal pools. Steam drifted like ghostly curtains around the islands, where volcanic heat met the cold of the water. The planet looked like a laboratory experiment left running too long. Messy, unpredictable, but full of energy. And below the waves, the dance continued. Submarine volcanoes still erupted constantly, adding new crust to the ocean floor and pushing older sections around. Some of that material collided with the cratons, sticking to their edges like geological bandages. Over millions of years, these collisions slowly stitched the planet's first protocontinents together, turning isolated islands into connected patches of stable land. The Earth was learning the art of assembly. These early land masses weren't hospitable. The atmosphere was still dense with carbon dioxide and methane. The sun, though weaker than today, baked the surface under a greenhouse haze. Rainstorms were acidic, carving ruts and pits into the rock. The tides, influenced by a moon much closer than it is now, were massive, waves hundreds of meters tall that constantly battered the shorelines. Yet these lands stood firm, anchored by their buoyant crust and strengthened by repeated cycles of melting and reformation. And as they endured, they began to accumulate a kind of geological wisdom. The constant recycling of rock brought new minerals to the surface, enriching the crust with elements like aluminum, potassium, and sodium, ingredients that would one day shape soils and nourish ecosystems. Without these early episodes of crust formation, the continents we know today, rich, complex, and full of variety, would never have existed. In a way, these first rocks rising above the ocean were Earth's first attempt at permanence. They represented the planet's shift from fluid chaos to structured complexity. The world was no longer just water and fire. It now had something solid, something that could endure through time. So the next time you pick up a rock, think of those first cratons. They were the planet's first breath of stability, the prototypes for everything that came after: mountains, deserts, continents, and the very ground beneath your feet. In their rough, scarred surfaces lay the blueprint of our world. The ocean world had given birth to its first bones, and now, for the first time, Earth could stand, if only on a few tiny toes poking through the waves. Once Earth had managed to push its first rocky islands above the waves, it encountered a rather awkward problem: gravity. Those newborn patches of land, no matter how proud they stood above the water, were still riding on a sea of molten rock. The crust beneath them was thin, hot, and unstable. If they were too heavy, they'd sink. If they were too light, they'd crack. The planet had to figure out how to keep its islands from constantly disappearing under the waves, like toast that couldn't stay above the soup. This was the era when Earth learned the art of balance, not the graceful kind you practice in yoga, but the deep geological equilibrium between mass and flotation known as isostasy. It's a concept simple enough to explain with a bathtub. Drop in a wooden plank, and it floats. Press down, and it dips. Let go, and it rises again. Continents, believe it or not, behave the same way. Enormous slabs of crust floating on the viscous mantle beneath. It's not fast or elegant, but it works. The oceanic crust, made mostly of basalt, was dense and heavy, formed from solidified lava that hugged the planet tightly. But when parts of the mantle melted differently, forming lighter, silica-rich magma, those sections became buoyant. As they cooled, they hardened into granite, the same kind of rock you'd find in mountain cores today. Granite was the secret ingredient. Light enough to stay afloat, sturdy enough to resist erosion, and chemically distinct enough to last. It was the planet's way of saying, let's make this permanent. At first, it was a delicate and dangerous process. The mantle below was still restless, its heat trying to reclaim what the crust had stolen. Each time a piece of granite-rich crust thickened, it pressed downward, pushing into the mantle until it reached the point where the upward buoyant force matched its weight. Only then could it float stably, a balance as subtle as a tightrope act performed in slow motion over millions of years. And yet, this was no static equilibrium. The crust rose and fell like a living thing, flexing under its own mass. When erosion wore down the peaks, the land rose slightly in response, like a sponge puffing up when pressure eases. When new layers of volcanic rock piled up, the crust sank a bit to compensate. The planet had developed a self-regulating system, one that constantly adjusted to maintain balance. It was as if Earth had learned how to breathe, slowly, deeply, through the rise and fall of its crust. This balancing act wasn't just a matter of staying afloat. It shaped the planet's entire future landscape. As buoyant crust formed thicker roots into the mantle, it created the foundations of stable land masses that could survive for billions of years. These roots, sometimes stretching tens of kilometers deep, acted like keels on a ship, keeping the land steady even as the mantle currents swirled beneath. They gave the continents weight without making them sink, anchoring them through time. The physics behind it was exquisite. Beneath each continent, pressure built up as the crust pressed downward into the mantle. But because the crust was less dense, the mantle pushed back, supporting it like a hand under a floating raft. Where mountains rose, their weight drove the crust deeper. Where erosion carved them down, the crust rebounded upward. This phenomenon, called isostatic rebound, continues even today, a quiet reminder that the Earth is never truly still. The early continents, or what passed for them, went through endless cycles of this buoyant adjustment. Some sank partially back into the mantle, only to be reborn later through new volcanic activity. Others grew thicker through collisions with neighboring cratons, fusing into more stable blocks of rock. Over time, the balance improved. the crust strengthened, and the land stopped behaving like a nervous swimmer treading water. The continents had learned how to float with confidence. Meanwhile, this dance between buoyancy and gravity began influencing other systems too. As land started staying above sea level for longer periods, weathering and erosion took on new roles. Rain and wind could now work their slow artistry, breaking down rock, releasing minerals, and feeding the ocean with nutrients. In turn, those nutrients began to alter ocean chemistry, paving the way for biological innovation. The simple act of keeping continents afloat had ripple effects that would eventually support life itself. It's fascinating to think that the stability of your nearest mountain range depends on a physics lesson written deep within the mantle billions of years ago. Every granite outcrop, every plateau, every dry stretch of desert stands where it does because of this invisible balance. The crust floats on a sea of semi-molten rock. Not by magic, but because of a precise negotiation between gravity and buoyancy, one that Earth worked out long before any human ever tried to build a ship. Of course, balance didn't mean peace. The mantle below remained in constant motion, its convection currents pushing and pulling on the crust. In some places, the crust buckled and rose. In others, it cracked and fell. The result was the first large-scale topography, ridges, plateaus, and deep ocean basins. For the first time, Earth wasn't just blue and flat. It had contours, highs and lows, a beginning of shape. As the continents grew thicker and their buoyant roots sank deeper into the mantle, the balance stabilized further. The planet's surface became a patchwork of floating plates, each supported by the viscous rock below. It was a precarious balance, yes, but it was also resilient, one that would allow mountains to rise, oceans to deepen, and life to eventually find niches everywhere from the seafloor to the sky. In the grand view of cosmic history, it's remarkable. A planet that began as molten chaos taught itself to balance, to rise and fall with grace. Earth's continents became not just passengers but dancers in a slow, eternal ballet, buoyed by invisible forces, held aloft by the very physics that once threatened to swallow them whole. So the next time you stand on solid ground, remember, it's only solid because Earth never stopped learning how to float. When the first continents began poking their rocky heads above the waves, Earth's climate was already deep in the middle of a high-stakes balancing act. The planet had cooled enough for oceans to form, but not enough to relax. The atmosphere was thick, heavy with gases that would make modern air look like a delicate souffle. The sun, still faint and moody in its youth, provided only about 70% of the light and warmth it does today, which should have frozen the planet solid. And yet, it didn't. Somehow, against all odds, Earth stayed warm enough to keep its oceans liquid, and it was the planet's first great climate riddle. How did a faint sun shine on a not frozen Earth? The answer was in the sky, or rather, in what filled it. Carbon dioxide, methane, ammonia, and water vapor blanketed the young planet, trapping heat like a planetary greenhouse. Volcanic eruptions belched out endless waves of gas, and with no plants or oceans yet capable of balancing things out, those gases simply lingered. The result was a steamy, high-pressure atmosphere that turned the planet into a sauna floating in space. If early Earth had a motto, It might have been sweat first, evolve later. The oceans, vast and newly formed, played the role of both villain and hero in this climate story. Water, as it turns out, is a climate control freak. It absorbs, reflects, and redistributes heat with a skill that no human-made system can rival. But with so much of it covering the planet, sunlight had a hard time reaching the depths. The top layers warmed while the deep ocean remained cold, creating powerful convection currents that churned ceaselessly. This constant mixing moved heat around, but it also stirred up gases and minerals from the seafloor, feeding a complex chemical dance between ocean and atmosphere. Carbon dioxide was one of the main characters in this dance. It dissolved easily in the ocean, where it reacted with water to form carbonic acid, a weak but relentless chemical that began slowly eating away at the newly exposed rocks on the seafloor and the earliest patches of land. That reaction pulled carbon out of the atmosphere and locked it into minerals, an early and entirely unintentional version of carbon capture. The planet, without knowing it, had started experimenting with climate regulation. But chemistry alone wasn't running the show anymore. Deep within the ocean's shadows, life, simple, microbial, and stubborn, had joined the cast. These early microbes were nothing flashy, just microscopic bubbles of chemistry wrapped in membranes. Yet they had a knack for turning their environment into a laboratory. Some learned to harness chemical energy from minerals near hydrothermal vents, releasing new gases into the water. Others, through metabolic quirks, began producing methane, a greenhouse gas even more potent than carbon dioxide. The atmosphere became a microbial mood swing, oscillating between steamy and scorching. This microbial meddling had huge consequences. Methane helped trap heat more efficiently than carbon dioxide, keeping the planet from freezing even under the dim sun. But it also made the atmosphere reactive and unstable. Lightning and ultraviolet light from space frequently set off wild photochemical reactions, breaking apart gases and creating new ones. Layers of haze may have formed high in the atmosphere, organic smog, essentially, that dimmed sunlight but kept the warmth in. It was a feedback loop of chaos that somehow produced stability. Meanwhile, the planet's surface began to experience its first subtle hints of climate zones. Around volcanic islands and ridges, warm currents formed, circulating nutrients through the water. In other regions, cooler waters sank, dragging dissolved gases into the deep. These early thermal gradients became the first whispers of weather, primitive wind patterns, gentle currents, and storms that passed like ghostly rehearsals for the climate systems we know today. And through it all, the carbon cycle, that great planetary accountant, was getting started. Volcanic outgassing added carbon to the air. Rainfall and weathering removed it. The oceans stored and shuffled it. Eventually, equilibrium emerged. The amount of carbon entering the atmosphere roughly matched the amount being pulled out. It was never perfect, but it was good enough to keep temperatures within the narrow window that allowed liquid water to persist. Earth, without intention or intelligence, had stumbled into climate self-regulation, a feedback mechanism that would become one of its greatest survival traits. Still, stability came at a price. The heavy greenhouse atmosphere meant the planet's surface was cloaked in a constant fog. The sky would have appeared orange or copper the horizon blurred by haze. There were no blue skies yet, no bright sunrises. Light filtered through in ghostly bands, giving the oceans an eerie, dim glow. If you'd looked up then, you wouldn't have seen the stars. You'd have seen the future ingredients of weather brewing above your head. Beneath that murky light, life continued to stir. Some microbes began adapting to new niches, forming mats along shallow seafloors and exhaling gases that would slowly start to shift the atmospheric balance. In doing so, they accidentally became the planet's first climate engineers, microscopic agents tweaking the chemical thermostat of the entire world. They didn't plan it, of course, they were just trying to survive. But in their quest to keep their tiny ecosystems stable, they began changing the global environment. This was the dawn of feedback, the idea that life and planet could shape each other. The atmosphere influenced the ocean influenced the crust, and the crust influenced life, which then altered the atmosphere again. The cycle had begun. Earth was no longer a passive ball of rock and water. It was a dynamic, responsive system. The irony, of course, is that this delicate dance between gases, oceans, and life, this natural, ancient climate engineering, would one day be rediscovered by a clever species that thought it had invented it. But billions of years before humans ever built a power plant or measured a degree, microbes were already managing planetary temperature like professionals. So when you think about climate control, remember, Earth wrote that manual long ago. The trick wasn't to make the planet static. It was to keep it just unstable enough to evolve. That fragile balance between heat and cold, between greenhouse and icehouse, between life and chemistry, became the secret rhythm that has kept Earth habitable ever since. Long before trees shaded continents or coral reefs shimmered with color, life made its first quiet stand in the deep. There was no land to crawl onto, no sunlight to bathe in, and certainly no oxygen to breathe. The surface of the ocean was a harsh place, bombarded by ultraviolet radiation and pelted with meteors from a still-cluttered solar system. But far below, on the dark sea floor, life found refuge. It was here, in the deep shadows of hydrothermal vents and volcanic ridges, that Earth's first ecosystems took root, invisible, alien, and astonishingly tenacious. These early pioneers weren't plants or animals, or even anything remotely complex. They were microbes, simple, single-celled organisms that looked more like tiny bubbles of slime than anything alive. And yet, they were masters of survival. They didn't need sunlight or oxygen. Instead, they drew energy straight from chemistry, using minerals spewed by volcanic vents like ingredients in a recipe for existence. They fed on sulfur, iron, and hydrogen, performing molecular gymnastics that powered their tiny metabolisms. In other words, life began not with light, but with chemistry. Imagine those first microbial colonies clinging to rocky outcrops near the vents. The water around them shimmered with heat, sometimes near boiling, and was rich with minerals. Superheated plumes rose like smoke, turning the surrounding ocean into a swirling cocktail of elements. These microbes gathered into slimy mats, growing layer upon layer over time, forming sticky carpets that blanketed the seafloor. They were the planet's first communities, each microbe playing its own microscopic role. Some produced food through chemical reactions, Others scavenged the leftovers. It was a microbial city built on teamwork and thermodynamics. This deep-sea world was both harsh and nurturing. The pressure was immense, hundreds of times what we feel at the surface, but that same pressure kept the water from boiling away. The temperature gradients around the vents, hot at the center, cold at the edges, created zones where chemistry could thrive. Like cosmic Goldilocks zones, some spots were too hot, some too cold, but a few were just right. Those perfect little niches became the first stable habitats on Earth. What's fascinating is that these early ecosystems operated entirely without sunlight. On the modern Earth, most life depends on photosynthesis, but here, in the dark abyss, life relied on chemosynthesis. Microbes used chemical reactions to build organic molecules, turning carbon dioxide and hydrogen sulfide into food. It was metabolism before photosynthesis. The universe discovering that energy could flow through life without ever seeing the sun. Over time, these microbial mats expanded beyond the vents, spreading across the seafloor. They grew on volcanic ridges, around cracks in the crust, and along underwater mountain chains. As they multiplied, they began leaving behind traces of their activity, thin mineral layers that recorded their presence like fingerprints in stone. In some places, the interaction between life and minerals produced structures resembling primitive reefs, though instead of corals, they were made of mineralized slime. These were the first ecosystems to shape geology, quietly altering the chemistry of the ocean floor. Within these mats, life diversified. Microbes competed, adapted, and swapped genes, the earliest forms of evolution playing out in microscopic time. Some developed thicker membranes to withstand heat. Others learned to store energy more efficiently. A few found ways to live near the cooler fringes of the vent fields, pioneering new territories. This slow expansion laid the groundwork for biological complexity. Life learning, molecule by molecule, how to survive in new environments. Occasionally, vents would die out, cutting off the supply of chemical energy. When that happened, entire microbial colonies perished. A cycle of creation and collapse that mirrored the rise and fall of civilizations billions of years later. But each collapse left behind traces of organic material, seeding the surrounding ocean with nutrients. Other microbes would drift in, colonize, and start the cycle anew. Life was stubborn, patient, and infinitely resourceful. Away from the vents, other forms of life were experimenting too. Some microbes began living near the surface of the water, where faint sunlight filtered through the haze. They weren't using it yet, but evolution was taking notes. Others discovered how to extract energy from iron or ammonia dissolved in seawater, expanding the boundaries of what food could mean. It was a time of biological improvisation, an era of trial and error played out over unimaginable spans of time. The seafloor itself wasn't passive in all this. The interactions between microbial colonies and the rock beneath them began to alter the crust. As microbes metabolized sulfur and metals, they changed the chemistry of their environment, dissolving some minerals and precipitating others. Over millions of years, this microbial alchemy transformed the seafloor into a patchwork of biological and geological textures. Life sculpting the planet long before animals ever existed. and though there were no predators, no plants, and no visible movement, the ocean floor was alive in a subtle, collective rhythm. Chemical gradients pulsed through the water, vent plumes rose and fell, and microbial communities expanded and retreated in tune with the planet's slow breathing. It was a world where life didn't roar or bloom. It simmered. If you could somehow dive there now, back to that time, it wouldn't look like a scene from a nature documentary. There would be no colorful coral, no darting fish, just darkness broken by shimmering vent light and the faint, ghostly shimmer of microbial mats waving in the thermal currents. It would look like the aftermath of creation, quiet, eerie, and full of potential. These early seafloor ecosystems didn't just survive, they rewrote the planet's chemistry. They released gases into the ocean and atmosphere, gradually tweaking the balance of carbon and sulfur. They helped cool the planet by trapping carbon in minerals and sediments. In short, they began engineering the environment to make it more stable, a habit life has never quite given up. So, while the surface of early Earth was still barren and stormy, the deep ocean was thriving with unseen life. The stage for biological history was set not on dry land, but in the dark beneath the waves, where heat met chemistry, and chemistry met persistence. There, in the quiet hum of the sea floor, life began writing the first chapters of its epic, one molecule at a time, one vent at a time, in the world's strangest and slimiest neighborhood. When you picture the earliest days of Earth, you might imagine fiery volcanoes, roiling oceans, and skies thick with storm clouds. But what if I told you that most of what we know about that chaotic era comes not from giant mountains or vast layers of rock, but from crystals so small they could hide inside a grain of sand? The history of our planet's beginnings is written not in continents, but in tiny, glittering witnesses called zircons, fragments of Earth's memory that somehow survived 4.5 billion years of planetary drama. Zircons are the introverts of the mineral world, quiet, tough, and impossible to get rid of. They form when molten rock cools and solidifies, trapping within their crystal structure a record of the conditions around them, the temperature, the pressure, even the chemistry of the environment. Each zircon is like a geological USB drive, storing data from a time when the planet was still deciding what kind of world it wanted to be. The oldest zircons ever found come from a place called the Jack Hills in Western Australia, a landscape that looks humble enough, rolling terrain, dry riverbeds, and scattered stones. But within those stones are microscopic crystals that predate any known rock formation on Earth. These zircons are roughly 4.4 billion years old, meaning they formed when Earth was just 100 million years past its creation. To put that in perspective, if the planet's entire history were compressed into a single day, these zircons would have appeared around 03 a.m., right after Earth's birth cry. When scientists first dated them, they were astonished. Nothing that old was supposed to exist. The early Earth, according to all logic, should have been too violent for minerals to survive. Yet here they were, perfectly formed, ancient crystals, older than any mountain, older than any ocean floor. It was as if the planet had left behind a few tiny souvenirs before tearing everything else down and rebuilding. But age wasn't their only secret. When researchers examined the isotopic signatures trapped inside these zircons, specifically the ratios of oxygen isotopes, they found something even more shocking. The chemical pattern suggested that the rocks from which these zircons formed had interacted with liquid water. That meant that as early as 4.3 billion years ago, Earth already had oceans. In other words, the blue planet we know wasn't a late development. It was part of the story almost from the beginning. That discovery completely reshaped our understanding of Earth's infancy. Before the zircons told their tale, most scientists believed the planet's surface remained molten for hundreds of millions of years after its formation. The assumption was that constant bombardment by asteroids and comets kept Earth too hot for stable crust or liquid water. But the zircons whispered a different story, one of a world that cooled faster, developed a solid crust early, and wore a thin blue veil of ocean while the rest of the solar system was still smoldering. These crystals also offered clues about the chemistry of early crust. Their trace elements showed that the rock from which they crystallized was similar to granite. The same light, buoyant rock that now makes up continents. That hinted that some form of continental crust may have existed billions of years earlier than previously thought. The continents might have started as tiny, scattered seeds long before they grew into the grand landmasses we know. Once again, zircons proved they were more than pretty crystals. They were storytellers, and they told those stories with remarkable precision. Each zircon contains atoms of uranium, which slowly decay into lead at a predictable rate. By measuring the ratio of uranium to lead, scientists can date each crystal to within a few million years, a rounding error on the scale of deep time. It's like finding a watch that's been ticking since the dawn of the planet and realizing it's still keeping time. Of course, zircons didn't survive unscathed. Many have endured being melted, reburied, and recycled through the crust multiple times. Yet they remain stubbornly intact, their inner chemistry shielded by the strength of their crystalline lattice. It's as if they were built with a do-not-erase feature long before anyone knew how to read them. Beyond their beauty and endurance, zircons are remarkable for another reason. They give us a rare glimpse of a world we can never see. There are no preserved rocks from Earth's first 500 million years. The crust from that era has long since been swallowed by the mantle, or transformed beyond recognition. Without zircons, our knowledge of that lost time would be nothing but speculation. These tiny crystals are the last surviving witnesses of a vanished Earth, fragments of an ancient reality that even time couldn't completely erase. Every so often, new zircons turn up in unexpected places: sedimentary rocks in Greenland, metamorphic belts in Canada, or volcanic debris scattered across old terrains. Each discovery adds a line or two to the planet's biography. Some zircons suggest periods of cooling and stability. Others hint at catastrophic impacts that melted the crust and started the cycle over again. Taken together, they paint a portrait of a restless world, constantly changing but never starting entirely from scratch. In a way, zircons are the ultimate storytellers of resilience. They were forged in fire, reshaped by pressure, and buried under the weight of time. Yet they still sparkle with secrets. Every one of them holds a microscopic snapshot of a world that looked nothing like ours, a planet young, wet, and volatile, already flirting with the ingredients of life. So the next time you see a gemstone glittering under the light, remember that somewhere in a lab drawer sits a dull little crystal that's seen more history than every diamond on Earth combined. It's the mineral that watched oceans form, volcanoes rise, and continents begin their slow dance. Zircons are not just minerals, they're memories. And, thanks to them, we know that our world, even in its fiery youth, was already dreaming in blue. There was a time when Earth's surface was quiet, or at least it looked that way. The oceans stretched endlessly, dotted here and there with small rocky islands that barely broke the surface. Beneath this calm facade, however, the mantle was stirring. Heat trapped deep within the planet had been rising for eons, pressing against the base of the crust like water boiling beneath a lid. Eventually, the pressure became too much. Cracks began to widen. Molten rock surged upward, and the crust started to shift. Earth's still surface was about to wake up. This was the birth of plate tectonics, the geological revolution that turned a static world into a living, moving planet. To the untrained eye, it might have seemed slow, even lazy, but in geologic terms, it was a frenzy. Massive slabs of crust began to slide past, crash into, and pull away from one another, reshaping the face of the planet piece by piece. Earth, after billions of years of simmering quietly, had discovered motion, and it never stopped. The driving force behind this awakening came from deep within the mantle. Heat from radioactive decay in Earth's interior created powerful convection currents, streams of molten rock circulating slowly but relentlessly. Where the currents rose, they pushed against the crust, cracking it apart and forming mid-ocean ridges. Where they sank, they dragged parts of the crust downward, recycling it into the depths. This process, creation and destruction, push and pull, became the planet's heartbeat. At the time, the crust wasn't a uniform shell, but a patchwork quilt of thick, buoyant continental fragments and thinner, denser oceanic plates. The oceanic plates were heavy, rich in iron and magnesium, while the continental bits were lighter and thicker, floating higher on the mantle like rafts on lava. When these plates met, the heavier ones slipped beneath the lighter ones in a process known as subduction, a slow-motion descent into oblivion that melted rock and fueled volcanic eruptions. Every collision reshaped the planet. Two continental fragments might meet and crumple, lifting mountains where once there was only sea. Other times, a piece of oceanic crust would dive under a continental edge, dragging down seafloor sediments and forging volcanic arcs above. Over millions of years, these forces stitched the planet's surface into a dynamic mosaic, a world that made and remade itself through constant movement. It's hard to overstate how revolutionary this change was. Before plate tectonics, Earth's crust had been relatively static, molten, soft, but not organized. Once the plates began to move, the planet gained a new dimension of behavior. It could recycle itself. Old crust didn't simply erode and disappear, it was reborn as new crust elsewhere. Volcanoes spewed fresh rock onto the ocean floor, creating ridges that spread apart like scars healing in reverse. Meanwhile, trenches marked the graveyards of older crust, where it was swallowed back into the mantle to melt and start again. The earliest continents, Those small cratons that had once floated aimlessly now began to converge. Some collided and merged into larger land masses. Others broke apart and drifted away again. The result was a geological dance that continues to this day. Land wasn't just rising anymore, it was moving. Earth had invented its own form of geology-powered continental drift, a kind of planetary shuffle that would go on shaping climates, ecosystems, and even the course of life itself. As these massive slabs moved, they created new geological wonders. Mountain ranges rose where plates collided, deep trenches carved the ocean floor where they diverged, and volcanoes erupted along subduction zones, releasing gases that altered the atmosphere. The air itself began to reflect the rhythm of the moving crust. Volcanic carbon dioxide thickened the greenhouse effect, while weathering on newly raised mountains helped pull it back down, regulating the planet's temperature in a long, slow feedback loop. Plate tectonics also transformed the way water and minerals cycled through the Earth. As plates dove into the mantle, they carried sediments and seawater with them. This recycled water helped melt rock deep below, making the mantle more dynamic and sustaining volcanism over geological time. Without this process, Earth's interior might have cooled and hardened, like the crust of a stale pie. Instead, tectonics kept the planet geologically alive, always reshaping, always renewing. Over time, this motion built larger and more stable continental cores. When fragments collided, they thickened the crust and formed new cratons, ancient, stable pieces of land that would become the seeds of future continents. These cratons locked together in shifting alliances, forming the first supercontinents long before the famous Pangaea ever existed. Each one would rise, drift, and break apart again, leaving behind a legacy of mountains, valleys, and newly mixed rock. The energy of these tectonic shifts also helped sustain Earth's magnetic field. Movement of molten iron in the core, aided by the cooling and convection cycles above, kept the magnetic dynamo spinning. This invisible shield protected the atmosphere from the solar wind, ensuring that Earth's precious air and oceans weren't stripped away. In a sense, plate tectonics didn't just build the planet's surface, it protected its soul. If you could watch it all unfold in fast forward, it would look like a time-lapse of sculpting and motion. Mountains rising like wrinkles in the crust, islands forming, oceans widening, and continents gliding across the globe like rafts in a slow but deliberate ballet. Each collision, each drift, each eruption was another brush stroke on the canvas of the Earth we know today. By setting its crust in motion, Earth became more than just another rocky planet. It became dynamic, self-correcting, and creative. Mars and Venus, similar in size but lacking active plate tectonics, grew stagnant, one frozen, the other smothered in heat. But Earth, restless and fidgety, found balance through movement. Its tectonic churn became the foundation for habitability, keeping the climate temperate, the air replenished, and the surface ever renewed. So, when you look at a mountain range or trace your finger along a map of continents, you're seeing the handiwork of this ancient awakening, a slow-motion revolution that never ended. The crust beneath your feet has journeyed across oceans, collided with neighbors, and been recycled countless times. Earth's tectonic heartbeat began billions of years ago, and it still echoes in every earthquake, every volcano, every tremor that reminds us that our planet, even now, refuses to sit still. After billions of years of planetary restlessness, the surface of Earth finally achieved something it had been working toward since its fiery birth: permanence. For eons, patches of crust had risen briefly above the waves only to sink again, swallowed by the mantle or drowned beneath the heavy ocean. But now one of them, a stubborn, buoyant mass of rock, refused to go back under. The first true continent had arrived. It wasn't the sprawling green landscape we might imagine. There were no trees, no soil, and certainly no birds greeting the dawn. This land was raw, a bare expanse of jagged rock and volcanic ridges, coated in minerals freshly exposed to the sky. If you stood there, your feet would crunch on brittle crystal fragments and the air around you would shimmer with heat and haze. The horizon stretched endlessly, broken only by pools of water collecting in craters and fissures. The smell would have been sharp and metallic, heavy with sulfur and the tang of wet stone. Yet, for all its desolation, it was beautiful. The first sunrise over this alien terrain must have been an extraordinary sight. As light touched the rock, the minerals within sparkled, flecks of quartz, feldspar, and mica reflecting in soft pink and orange hues. Steam rose from hot fissures as the sun's warmth met the still cooling crust, creating a fog that danced above the ground. It was as if the planet was taking its first visible breath, a sigh of release after its long, molten youth. Geologically speaking, this was the moment when buoyancy finally won. The continental crust, thicker and lighter than the basaltic crust beneath the oceans, had grown dense enough in structure and stable enough in shape to stay afloat indefinitely. Heat from the mantle continued to rise beneath it, but the balance between pressure, density, and cooling allowed this new land to hold its own. Earth, for the first time, had both ocean and continent, the beginnings of contrast, pattern, and complexity. These earliest continents were small by today's standards, perhaps no larger than modern islands. But they were transformative. Their emergence changed everything about how the planet worked, from the chemistry of the atmosphere to the behavior of the oceans. The exposed rock began interacting with air and rain, dissolving minerals and altering chemical balances that had been stable for hundreds of millions of years. The land became a new laboratory for reactions, a new stage for geology's experiments. Rain fell constantly in those early Mays, washing across the bare stone. Each droplet carried traces of carbon dioxide, forming weak acids that began to dissolve the rock, creating the planet's first true weathering. Rivers and streams formed, shallow but persistent, carrying dissolved minerals back into the oceans. The water darkened with sediments, iron, silica, and calcium, each grain a piece of land's contribution to the evolving planet. The carbon drawn from the atmosphere into the water began to cool the planet further, a subtle but crucial shift that set the stage for a more temperate Earth. Volcanoes continued to erupt across the new land, releasing clouds of ash and gas that mingled with the atmosphere. The cycles of eruption and erosion became intertwined. The surface renewed itself in bursts of fire and smoothed itself in waves of rain. With each eruption, the crust thickened. With each downpour, it reshaped. The land wasn't static. It was alive in its own slow geological rhythm. Meanwhile, life in the oceans was watching, though watching might be too generous a term for the chemical pioneers that existed then. Microbial mats, already thriving around hydrothermal vents and volcanic ridges, began exploring shallower waters near the new coastlines. Here, sunlight reached the seafloor, providing a new kind of energy. The boundary between land and sea became a place of innovation, a meeting point of minerals, light, and molecules. In those shallow pools and tidal flats, life found fresh chemistry to play with. And the land, though lifeless, played its part. The minerals exposed to air began releasing elements like phosphorus and potassium, nutrients that would later become vital to living cells. Wind and water carried those nutrients into the ocean, enriching it and feeding microbial communities. In a way, the continent was feeding the sea, creating conditions that would eventually support an explosion of biodiversity. The appearance of land also marked a visual transformation of the planet itself. From space, had anyone been there to look, Earth was no longer a uniform blue sphere. It had texture, patches of brown and gray breaking through the endless blue, edges shimmering with vapor where sea met shore. The planet had become more dynamic, more sculpted. The rise of that first continent turned Earth into something recognizable, a world with geography. Over time, the first continent grew as molten rock continued to well up from below, cooling and hardening along its edges. Smaller fragments collided with it, fusing into larger land masses. Faults cracked, mountains rose, and valleys formed. Each geological movement added layers to the planet's identity. The once smooth ocean world now had features, peaks, plateaus, plains, all sculpted by the push and pull of tectonic forces. This transformation also introduced the concept of permanence in the planetary sense. The oceans had always been in motion, their surfaces fleeting and formless. But land could endure. Even when eroded, its materials remained part of the cycle, recycled into new rock or swept into sedimentary layers that recorded the passage of time. Earth, for the first time, began keeping long-term records of itself in stone. The rising of the first continent was, in many ways, the planet's declaration of maturity. It marked the transition from chaos to structure, from simplicity to complexity. The bare rock might have looked barren, but it was the foundation for everything to come. Soil, rivers, forests, civilizations. Every mountain range, every desert, every city in history would trace its lineage back to that first stubborn piece of a crust that refused to sink. If Earth could remember that moment, perhaps it would recall it as its first sense of balance, a turning point when the endless ocean met something solid and both learned to coexist. It was the dawn of contrast, the birth of landscape, and the quiet beginning of everything that makes our planet what it is today. The first continent didn't just rise from the sea, it rose into history. The moment dry land became a permanent fixture on Earth, the planet's chemistry, and life itself, entered a new chapter. For billions of years, the oceans had been the stage, the sole arena for biology's slow experimentation. But now, The appearance of continents set off a cascade of changes that would transform the world from a quiet blue sphere into a vibrant, self-sustaining ecosystem. The rise of land didn't just redraw the map. It rewrote the rules of planetary evolution. At first, the land was raw and lifeless, bare rock shimmering under a harsh sun. But rock is never truly still. The moment it met air and water, it began to change. Every raindrop that fell carried a hint of carbon dioxide, forming weak carbonic acid. As it struck the rock, that acid reacted with minerals, breaking them down into ions that drifted away with runoff. It was the planet's first act of large-scale chemical weathering, slow, patient, and incredibly powerful. Over millions of years, these reactions chewed through mountains and plateaus, creating sediments that flowed back into the oceans. Those sediments carried with them a cocktail of elements: phosphorus, calcium, silicon, and iron. Nutrients that were rare in the open ocean but essential for life. Once in the sea, they became the building blocks for new biochemical reactions. Microbes, already thriving in the shallow coastal waters, suddenly had access to a buffet of raw material. With more phosphorus came more energy for cell metabolism. With more iron came faster growth. What had once been a sparse microbial world began to bloom. This flow of nutrients marked the beginning of the planet's first global feedback loop between geology and biology. As life consumed minerals and altered chemical balances, it changed how the planet's systems behaved. The oceans, now infused with fresh inputs from land, began to host more complex communities of microorganisms. Layers of microbial mats thickened across shallow seafloors, and for the first time, biological productivity started influencing atmospheric chemistry. Life and landscape had entered a partnership. Rivers, those restless sculptors of the land, became the key intermediaries in this planetary collaboration. They carved channels through the rock, grinding mountains into dust, and carried that dust into deltas and ocean basins. Each river acted like a conveyor belt, moving nutrients from land to sea. The more erosion occurred, the more food flowed to marine ecosystems. Even without plants or animals on land yet, the mere existence of rivers reshaped the balance of life below the waves. Weathering also had a surprising side effect: climate regulation. When rain reacted with exposed rock, it pulled carbon dioxide out of the atmosphere and locked it away in carbonate minerals that settled to the seafloor. This gradual removal of greenhouse gases helped cool the planet, preventing the kind of runaway heating that had once plagued Earth's earlier years. The continents, in essence, became part of a planetary thermostat. As mountains rose and eroded, they helped balance the climate, a geological seesaw that continues even today. With cooling temperatures and nutrient-rich seas, the biosphere entered a new phase of expansion. Microbes diversified wildly, adapting to new chemical niches. Some thrived in oxygen-poor environments, while others began harnessing sunlight more efficiently, setting the stage for photosynthesis to take off. The chemistry of the ocean shifted again, and with it, the atmosphere slowly began to change. Oxygen, once a trace gas, started to accumulate, a subtle but profound ripple that would eventually reshape the entire planet. And as the continents grew, they began influencing the movement of heat and water around the globe. air currents shifted, winds formed, and rain patterns changed. For the first time, weather had geography. The sun heated land faster than water, creating pressure differences that generated the earliest climate zones. The atmosphere, once uniform and static, now swirled with dynamic systems, trade winds, monsoons, and protostorms that sculpted both land and sea. The continents also changed the rhythm of the carbon and sulfur cycles. Volcanoes erupted along continental margins, releasing gases that fed into the air, while sediments trapped in ocean trenches recycled back into the mantle. These interactions created a long-term balance between the deep Earth and the surface, a planetary dialogue that would keep the biosphere running for billions of years. Without continents, that balance would never have stabilized. It's easy to overlook how something as inert as rock could transform a living world. But on the scale of deep time, rock was anything but inert. It crumbled, reacted, and fed the oceans, all while setting the stage for biological innovation. The continents gave life the scaffolding it needed, not just chemically, but physically. Tidal pools, lagoons, and shorelines became laboratories for evolution, places where molecules could interact, concentrate, and eventually become more complex. If the rise of land had a soundtrack, it would have been the sound of rain on stone, rivers cutting through canyons, and waves grinding rock into sand. Each sound was a step in Earth's long transformation from sterile rock to fertile planet. Over millions of years, the effects compounded. As continents grew larger and more stable, erosion increased, and nutrient delivery accelerated. The oceans became bustling hubs of biochemical activity. Diversity exploded, not in a single burst, but through countless local experiments. New metabolic tricks, new chemical pathways, new adaptations. Life was learning to take advantage of what the land provided. And so, in a poetic twist, the continents that had once risen from the ocean began to feed the ocean in return. The land gave the sea its nutrients, the sea gave the air its oxygen, and the air gave the land its rain. It was an intricate, self-sustaining loop, the first planetary-scale cooperation between rock, water, and life. What began as barren stone had become the engine of vitality. Land, by merely existing, had turned a quiet ocean world into a restless, interconnected biosphere. It didn't just shape the surface of Earth, it transformed the heartbeat of the entire planet. From that moment forward, life and land would evolve together, partners in a never-ending story written in water, air, and stone. If you could rewind the universe and watch Earth's history play out in fast forward, you'd see a planet that learned to reinvent itself over and over again. From molten chaos to blue serenity, from oceanic emptiness to continents rising proud above the waves. It's a transformation so profound that it feels almost mythic. What began as a formless water world became a mosaic of continents and seas, a world not of one habitat, but of many, a world of worlds. The rise of the continents didn't just add land, it added diversity. Oceans are vast, but uniform. Land, on the other hand, is full of edges, contrasts, and microcosms, valleys, cliffs, mountains, and basins. With the first continents came topography, and with topography came variety. Temperature, light, wind, and water flow differed from one region to another, creating countless little environments where life could test new ideas. For the first time, evolution had a playground that wasn't just deep or shallow, it was textured. And Earth wasted no time turning that texture into possibility. Volcanic ridges became the first mountains, towering over plains of cooled lava. Ancient rivers cut into the crust, carving canyons that would one day carry the lifeblood of ecosystems. Rain pooled in depressions, forming lakes and wetlands that shimmered beneath an ever-changing sky. The planet that had once been smooth and monotone was now full of contrasts, dry and wet, high and low, calm and violent. The continents also gave the planet a kind of memory. Before their emergence, the ocean floor had constantly recycled itself, erased by tectonic churn every few 100 million years. But continental crust was thicker, more buoyant, and far more durable. It didn't sink easily. That meant it could preserve its own story. Layers of sediment, traces of atmosphere, fossils yet to come. The continents became Earth's library, storing the records of its geological and biological history. Over time, these continental blocks drifted and collided, fusing into larger land masses that we now call supercontinents. The first of them, may have formed as early as 3 billion years ago, a modest cluster of granite and basalt that floated on a restless mantle. Later came Kenorland, Columbia, Rodinia, Panocha, and eventually the famous Pangaea, each one an epic rearrangement of the planet's geography. These supercontinents broke apart and reunited in an endless cycle, their collisions building mountains and their separations spawning oceans. The Earth wasn't static. It pulsed, reshaping itself through time like a living organism renewing its skin. This perpetual motion had profound consequences. When continents collided, mountain ranges rose, exposing fresh rock that weathered and fed the oceans with nutrients. When they drifted apart, new coastlines appeared, providing habitats for marine life and regulating global temperatures. Every tectonic reshuffling rewired the climate and ocean circulation, which in turn shaped evolution. The continents acted like gears in a planetary machine, driving the rhythm of change that allowed life to adapt and thrive. Eventually, that diversity of environments made something extraordinary possible: the colonization of land. The first microbes crept onto wet rocks and mudflats, forming thin, greenish mats that clung to surfaces like living paint. Over countless generations, these pioneers learned to survive outside the ocean, paving the way for plants, fungi, and, much later, animals to follow. The continents, once barren, became lush and alive. Forests sprouted, rivers teemed with creatures, and the air grew rich with oxygen. A gas that had once been poison now turned into the breath of life. From a cosmic perspective, this was Earth's defining feature, the moment it stopped being just a planet and became a system, an organism in its own right. It wasn't merely sustaining life, it was co-evolving with it. The continents influenced the biosphere, and the biosphere, in turn, sculpted the continents. Roots cracked rock into soil, oxygen transformed minerals. Coral reefs grew along shorelines, building new land from the sea. The planet had become self-aware in a chemical sense, each process sensing, adjusting, and responding to the others. And through this dance of land and life, Earth achieved something no other known planet has: balance. The continents regulated temperature through weathering. Volcanoes renewed the atmosphere, and oceans distributed heat and nutrients. Feedback loops stabilized the climate, keeping it just chaotic enough for evolution, but not so extreme as to destroy it. It was an improbable harmony, fragile, dynamic, and endlessly creative. From space, the transformation was spectacular. The once featureless blue sphere now gleamed with browns, greens, and whites. Clouds spiraled over continents. Shadows played across mountains, and the patchwork of land and ocean reflected sunlight in shimmering patterns. Earth had become visually alive, a painting in motion, a world that could be recognized instantly for its vitality. The rise of the continents also changed how the planet interacted with the cosmos. The balance of land and sea affected how sunlight was absorbed and reflected, influencing everything from temperature to atmospheric circulation. Even the length of the day began to shift as tides tugged on continents and oceans alike. Earth was not a static rock orbiting the sun. It was a participant in its own cosmic choreography. And, perhaps most poetically, the continents made home possible. The very concept of standing on something solid, of belonging to a place, only existed because land did. Every mountain range, every desert, every field and forest traces its lineage back to that first stubborn piece of rock that broke the surface and refused to sink. Without it, there would be no landscapes to shape imagination, no soil to grow food, no place to call our own. So, when we look at Earth today, with its continents drifting slowly across the globe like ancient wanderers, we're witnessing the continuation of a story that began billions of years ago when the first land rose from the sea. From molten beginnings to shimmering oceans, from bare rock to thriving biomes, the planet has been on a long journey toward complexity and beauty. The continents didn't just give Earth structure. They gave it character. They turned a featureless ocean planet into a world of seasons, cycles, and life. What began as a blank blue sphere became a masterpiece of contrast and color, a place where chemistry learned to dream. Earth started as a water world, but in the end, it became something far more intricate, a world of worlds, where rock, water, air, and life are all parts of the same cosmic symphony. And somehow, against the vast silence of space, that music still plays on.